be here. It's a beautiful venue. I've never been up here before. And it's great to see members of our Santa Barbara community as well as colleagues and students. So, as Alan mentioned, my work is at the intersection of wireless communication and robotics. And so I'm going to give you a few samplers of some of the work that is going on in my lab. Okay, so communication signals are everywhere these days. We all want more connectivity, and as a result, we're bombarded by these signals, by cellular signals, by Wi-Fi signals. So can they do more than communication? Can they help us learn something about the environment or sense something about the environment? For instance, can I use Wi-Fi signal to, to count the number of people, to do crowd counting in this area? Or let's say in an office space, can I use Wi-Fi signal to figure out the spatial distribution of the people so I can optimize heating and cooling? These are sample Sonos speakers. Sonos is a smart speaker company in town. And these are their speakers. Can we use them at home? And these speakers learn something about us, where we are, so somehow they can optimize service to us. And these are our ground vehicles. Can they just move outside of this area and use just Wi-Fi to image through walls? So these are the problems we're interested in. And in this talk, I'm going to talk about two problems. First, imaging through walls with just Wi-Fi signals. And then counting and occupancy estimation with Wi-Fi signals. Now, on the robotics side, this is a great time for robotics. The idea of unmanned vehicles being part of our society and help us achieve tasks is not futuristic anymore. We've all heard about Amazon Primer that will hopefully soon drop our packages for us. And maybe soon we'll get to drive in a Google automated car. So what I'm going to talk about then is something at this intersection of robotics and communication, using robots and Wi-Fi to give X-ray vision to these unmanned vehicles. So let's look at the setup we have. So this is outside of our building. These are our drones. They're flying outside of the area. One of them is transmitting a signal. The other one is making measurements of the received signal. And let's say they move around this area a few times. They've just showed up here. They don't know anything about this area. But can they just move around the area a few times and image through walls, just with Wi-Fi? Okay? So let's take a look at this problem. Let's talk about why it's challenging. So, or why it's first maybe possible, I don't know. So, these are also our ground vehicles, and one of them is transmitting, the other one is receiving. This is the received power measurement that the receiving node is measuring, and that's something you can measure in very easily in any Wi-Fi device, let's say. And so these transmissions will interact with the objects in that area. And so as they go through objects, it's as if the objects are leaving their signatures on that transmission. But the impact of all these objects will get mixed up together in the received signal. And the information of these objects will get buried to the level that is as if there's not much information there. So the question we have is, how extractable is this information? And then I'm having unmanned vehicles. What kind of motions should they do outside of this area? What kind of motion patterns to make this area most observable? Okay? All right, so what I like to do here is talk a little bit about some of the challenges to enable this. So, first of all, as this wave goes through this area, we have to come up with a way to properly model the interaction. Second, we may not be able to collect as much measurements. And so we may not have really enough information to make any judgment about this area. And then dealing with unmanned vehicles, that in itself is challenging. There's always localization errors. And so let's say you have a little bit of wind and you're dealing with drones, that can throw off your measurements. So what I'm going to do in the next few minutes is I'm going to briefly talk about each of these challenges and give you a sense of how we go about addressing them. So let's talk about model. So I have a transmitter here and a receiver here. If I really want to write down the true wave equation, so this is, I know we're not going to go over any equations, but this is an electric, received electric field signal here. It's a very convoluted function of the objects. It's very nonlinear for one thing of this object. And so we really don't want to go that route of that level of detailed modeling. So our first challenge is there a way I can model this interaction that is simple enough, yet captures the information I need? So let me tell you a little bit about that. For instance, let's consider this simpler model. I have a transmitter here and a receiver here, and I'm just going to say, let's take a look at the straight line from the transmitter to the receiver, and just model the impact of the objects along that line on the reception. When there's a transmission, that transmission will interact with pretty much everything in this space. Or we're saying, let's not worry about them. The biggest impact could be mainly along this line of sight path. So that is what we call line of sight approximation. And it is valid if you really go to like X-ray frequencies, the true X-ray. But at these frequencies we're dealing with Wi-Fi, that is an approximation. But what this approximation does for us is gives us what we call here a linear model, a linear relationship from your measurements to the object information. These are the objects that are hidden and you want to image. And we like linear relationships. There are a lot of tools, mathematical tools, that we can take advantage of, or computational tools. So here, basically, these are my measurements. This is a linear expression relating them to my object information. There are other more extensive approximations that we also use. This Ritov model is another one. It results in a different linear expression, and it's a little bit more extensive, and it says, okay, I'm going to be a little bit more inclusive, not just the line of sight. Let's take into account the impact of the other objects, but with some approximations. So, now, in any modeling, the next part is to see, well, how well your models did. And so here is a real measurement, this blue line, and then here I have two approximations, the line of sight one, the black one, which you can see that at these high peaks, it matches the signal pretty well. But in these middle parts, the gap between the black and blue, is not negligible. And we don't expect perfect, results and modeling here. But as long as it's informative for what we want to do, that will be a good approximation. The red one is the other Ritov model, and you can see it's doing better than the black one. Here, it's matching the signal well, and also in this area, it's matching it better. Now, let's go to our second challenge. Our second challenge is dealing with the fact that we have a lot more unknowns than the measurements. So when these unmanned vehicles move around the area, they collect measurements. But the number of unknowns, which is basically related to the size of the area. Imagine that you take the size of the area and discretize it with little voxels, and you want to know the object information at every voxel. For instance, you may want to know, is there an object in that voxel or not, or is it empty? Or what is the material property, let's say, of that object? But when you look at the size of the unknown, it's a lot larger than the number of measurements that these robots can collect, because it takes a long time for them to fly around and collect measurements. So, how do we deal with that? Well, so here's how we deal with that, is that while the size of unknown is large, most signals around us are very compressible, meaning the information content is basically lies in a space much smaller than that original space. And that is a base for a lot of compression techniques out there. But here we're dealing with a little bit different problem. In compression, you take the signal, you measure it first, and then you compress it. But here, I don't have this signal, I'm trying to estimate it. And I want to take advantage of this fact that it is compressible in the sensing and estimation process. So, basically what we take advantage of is called sparse signal processing. Basically, there's a nice body of theories that tells you that you can sense signals in this compressed manner, basically. And so, basically, if you make a number of measurements and your area has certain properties, certain sparsity properties, you can take advantage of them and tell me the result, in this case the image of this area, with very little measurements. So these properties, what are these properties? For instance, we know that a lot of the areas are sparse in their spatial variations. For instance, here, I have floor for a long while with no changes, and then there's a jump up here to this, let's say, table. So the spatial variations in this area, we can say, has some sparsity. Can we take advantage of such things in our imaging process? So that's another thing that basically we take advantage of. And so we don't have to go through theories. Now, the last piece of this imaging is the path planning. So we're using unmanned vehicles. And when we use unmanned vehicles, it's as if I have several transmit-receive antenna positions along the route of this unmanned vehicle. And so that is really one key enabling factor, because if you don't have unmanned vehicles, the imaging we show, the imaging results we show, is not possible with Wi-Fi. The reason we've been able to show such imaging results with just Wi-Fi is because we're also using unmanned vehicles and taking advantage of the mobility. And the fact that I can create basically several antenna positions. By the way, feel free to interrupt and ask questions. So basically then, the main question here is that, well, what route should this robot take? Because different routes give me different antenna patterns. Is there any way I can optimize that? And so we spend a lot of times understanding that there's certain routes that make this job easier. I'm going to show you a sample of our routes at the moment for 3D imaging and tell you a little bit about how it's done. So here you can see there's a transmitter and receiver. Let's first look at this 2D version. That are basically taking these parallel routes. And these parallel routes are motivated by CT scan. This is how computer tomography is done. And so you can prove that these kind of routes are actually quite informative for this type of imaging. Now this is in 2D. What about when I go to 3D? So what we basically do is design routes that can capture the spatial changes, the variations in X, Y, and Z dimension. So we have a combination of these horizontal routes and these sloped routes. And basically at each of these angles, so we come up with a few angles. For instance, I'm showing here 0 and 45. Then the robots will basically do a series of horizontal and slope routes. Now, with all those, now let's take a look at some results. So basically, these three elements that I mentioned are the ingredients of our proposed approach. Our proposed approach is a tight integration of these three. And so let's take a look at some of our results. So this is an area, so this is what is here. These are brick walls, these are highly attenuating. Imaging through these are not easy. These guys move outside of this area, taking basically the routes that we proposed. And then you can see, so this is the ground truth. And this is how they imaged the area, basically. And so we can see that a lot of the details are preserved. Of course, we do not expect at all perfect imaging, but just the fact that they were able to image it at this level, that is very promising for us. So note that all the empty and full areas, they're all imaged. These robots didn't know anything about either the empty or the full spaces. And so everything is imaged with Wi-Fi measurements. Okay, so we also have a lot of results in also 2D with ground vehicles. I can show you some of those. These are some of our earlier results when we were imaging using ground vehicles in 2D. As these two robots taking a few routes, the image gets updated. The middle one, the color one, is basically an indication of material property, and this is an indication of if there's an object there or not. They're going to do 4 routes here, and we can see similarly that they're able to basically image the area well. So we're going to look at next a comparison between the image in this case and the ground truth. Here even the outer walls were all imaged with just Wi-Fi. And so this is the painful part of our work, building structures so that we can basically understand the improvements we make to our methodology. Here we've put 2 things inside these 2 blocks, and you can see they got imaged pretty well there. This is one of the lead PhD students on this project, Sandeep, and so he goes into to basically get imaged. And now, if you're talking about, go ahead.
A quick question about when you say 1.79% measurements, what does that refer to?
Excellent question. So that means the number of measurements they took as compared to the number of unknowns, that ratio was less than 2%.
Oh, okay.
That shows us how basically the lack of enough measurements, and if we didn't do some of these things that we're doing, there will be a lot of ambiguity basically. You won't be able to actually come up with one unique solution. So we're also dealing with a robot, so unmanned vehicles a lot of time have other sensors. For instance, they may have a laser scanner. And so can you use both of them? So laser scanner can image what is in front of it, and then this Wi-Fi can image what is through walls, and then the combination can be turned into a more powerful sensor. This is one of our early 2D images. This is a 2D area. And so if you only use laser scanners, the current technology, then you can't really say anything about here. But when you combine them, then basically you can image this area in these manners with different techniques that we've proposed. And so now, let me mention also a couple of applications that this may have in general. One possible application, more futuristic, but would be if, for instance, you can use something like that for health purposes. So I personally never like being radiated, so when you go to doctors and they always say, okay, let's get an x-ray, and I always argue with them. It would be great if, let's say at home, you can use the router and your phone, and let's say I just have an implant in my knee, and then I can move the phone with certain patterns, and I could see the progress of the screws or whatever they put in my knee. Now, we haven't done that. Is that doable or not? I can't say yet, but that will be a very good application. Go ahead.
Do you have any concerns about privacy with this technology? Because you can see through walls, that leaves a lot of room.
Yes, that's a very good question. Question we get a lot. So the question, well, so one thing is, with every technology, one has to be very careful. We really need to, at the same time, for every technology, come up with ways to make sure that it's used with integrity. And even some technology you don't even think about, like with drones flying now, that's actually a major concern because they come here and they start, looking through people's. Here, in terms of true wall, while it is true wall, at least at the moment, the resolution is not such that it could really see details of people and so on. But as we move forward, or with any other technology, one has to be always careful in parallel some standards or some procedures to make sure that it's used with integrity. So that's a very good question. Okay, so I've talked about this imaging through walls. I'm going to switch gears now to counting people, occupancy estimation. So I have colleagues in mechanical engineering, and they always used to tell me that, you know, heating and cooling optimization in buildings, that's an important problem. And so they use a variety of sensors, but then, you know, I started thinking, well, can we use Wi-Fi? And that's everywhere. Can that be used for estimating the occupancy, the number of people, maybe how fast they're moving, some attributes of how people move around in their space. Now, potential applications, so heating and cooling optimization. Apparently there's a lot of interest in retail business planning to count people. That's something I learned after our work came out. I got contacted by all these companies. Apparently stores and retails, they really want to know which products are more popular. So if they have a way of knowing which aisles are getting more populated, they really like that. Emergency evacuation, a way to evaluate in general, a fast way of saying how crowded an area is for the police force to evacuate an area. General smart home applications, smart city applications. These are all potential applications that can benefit from occupancy estimation. Now, typically when you look at occupancy estimation, the camera methods use cameras. And when you look at consumer reports, consumers really don't like it if stores use cameras to kind of track each person, you know, look at what they're shopping. So here we're going to use wireless signals, and in a passive way. So you don't have to carry a phone or anything. It's really not being connected to your device. It's rather by how your movements affected the signal. And in a way, so it's just going to give a collective feature of the crowd. So average speed of people in this area was this, or the total number of people is this, without really tracking any individual person. So in this case, this one really, this next technology is going to really preserve privacy. So now let's take a look at what we're interested in here. Let's say here, so here the robots are just carrying our Wi-Fi cards. There's no robotic element here. So there's a router here, and then there's the wireless LAN card receiving the signal. And so as we have people walking in this area, we can see the received signal measurement. Again, this is something very basic. You can measure it in any card very easily. And so as people walk, the signal goes up and down. The question is, can I just use this and just this? And tell me how many people there. And I notice people are zigzagging, crisscrossing, in the area can get reasonably crowded. And this signal seemingly doesn't really have any explicit correlation with the number of people. So the question is, does it implicitly carry a good amount of information on the occupancy?
So is it capturing when somebody crosses the line?
So basically it will drop when people cross. And as you see, that's an important feature. So basically, our goal here in this project was to understand how much information such a measurement will carry about number of people, speed of people, flow rate of people in between areas, all those occupancy features. So again, our first step is really, again, modeling. And we're not interested in a detailed modeling of the wave interaction with the occupants. That would be too prohibitive, too computationally complex. So we're looking at a simple modeling that is still informative, that captures the information we're looking for. For instance, when people cross the link, as it was mentioned, there will be a drop in the signal. And if multiple people cross at the same time, the drop would be more. So these drops here, for instance, are because these big drops here are because basically somebody crossed the link. Or here multiple people crossed the link at the same time. So that is information. So the question is how much information, and how is it explicitly related to what we're interested in estimating. Then, what if you don't cross the link? Still, you can affect the signal. By having the signal bouncing off of you, you act as a scatterer, and that will affect the received signal. So a lot of the variations up here are because of what we call multi-path, meaning the transmitted signal finds multiple paths to the receiver by bouncing off objects or other things, in this case, by occupants. Okay? So we're going to take advantage of these two in our modeling. Now let me show you these two phenomena a little bit more explicitly in this video. So this is what we call line of sight path. The person crossed. There is a big drop in the signal, but there's also could be another route. This person acting as a scatterer and basically resulting in in changes in the received signal. So basically what we've done is characterize these two mathematically and relate them to the number of people in the area or other features of occupants. For instance, just to give you a brief sense, so again, our modeling, and we're not going to go to details, but basically, our received signal is a combination of that line of sight part and that scattering part due to different objects, well, scattering part due to walking people, as well as the impact of the static objects. And then, basically, after some extensive mathematical derivation, what you can characterize is the following. And so let me go back to this figure. So here's the received signal. And so from this, you can plot a histogram of what percentage of the time the signal will get certain power or certain value. Now, theoretically, we mathematically characterize the same thing. And so now I have an experimental one, and then I have a theoretical one. And that theoretical one shows us exactly and explicitly how the number of people, or if the number of people would affect the measurement we have. And what we've seen is that actually the measurements are very sensitive to the number of people. And now we have the explicit relationship. And so then we compare these two PDFs, the histogram with the theoretical one, which we call a PDF, and we can estimate the number of people from there. Go ahead.
And where mathematically or graphically do you cross the multipath? Just from the environment itself, not from people?
You mean the objects? Excellent question. So it comes up in the formulation. So there are a couple of parameters that capture the impact of static objects. In this formulation I showed here, so what we did is you go to the area if there's nobody there and make a couple of measurements, and then you can estimate those parameters. Turn out in our later work that there are other methods that become a little bit more immune to needing so much to learn the impact of the static environment. But nevertheless, it's very important here that any prior measurement you have to do in the area has to be very minimal, because you don't want to go run extensive ones. So that is one thing that we ensure. And that, can you even do it in other areas? You don't have to do it in the same area. That's something we've shown that is actually possible. Very good question. Okay, so basically we have this histogram from the signal, and then the theoretical one that we characterize explicitly as a function of number of people, and then by comparing them, we can estimate the number of people. So basically that's what this derivation is summarizing. And now let's look at some real experiments. So we do a lot of experiments to validate our approach. Here again, so the robots are just carrying the cards. So transmitter, receiver, we have people walking, and you can see the update. These are measurements, not one after another, but we just put them together in the video like this. So there were separate instances. So there was a case with 5. It's not like they just kept increasing. That would have made it easier. But you can see that the number of people got estimated pretty well. Like 9 got estimated as 8, 7 as 7. Again, we're not looking for perfect, but is it informative and for applications? And what we are observing is that it could be quite informative. And scary that it can count. Now let's move to indoor. Indoor is always more challenging, again, because of we have more impact of static objects. And so you can see the area can get pretty crowded, people are zigzagging. but then it can still count the number of people pretty decently. And so we run a lot of experiments to basically, because one time maybe you're lucky, right? But we run several experiments to look at the how much error collectively we had over several experiments. So these are the CDF of estimation error, which is basically what percentage of the time you measured, like if you could do several experiments, what percentage of the time you measured we were 1 off, 1% off, and you're counting 2 people off, and so on. So here, for instance, we can see that in this experiment, for instance, near 90-some% of the time, we measured we were off just 2 people or less, basically, which indicates a good performance. And so we have other histograms as well, and so that's an important part of it to validate with several measurements. What about more people? So the main challenge with more people is getting more people, really, and that's what we found in our work. Just we put advertisement for students, we offer payment. I think UCSB students are too rich, you know. It's really hard to find people to come and work for our experiments. So here we found 20 people, and basically we have one link here, so one transmitter, one receiver. The area is like 21 by 10, so you can see that we did tests with 5, 10, 15, and 20 people, and they were estimated pretty well. Now we've extended, go ahead.
I'm assuming if you added more receivers, you might increase your accuracy, but
Absolutely.
But does your computational complexity go geometric at that point, or is it just a linear?
Very good question. Actually, I'm going to show you results with more links. No, it doesn't actually. It's computationally quite efficient, so it takes, once you collect the measurements, about a second or so of computation. So I did a couple of links, it's okay, yes. If we are doing extensive over a huge area, which we are looking into, then those are certainly concerns, and we're studying those. But I'm going to show you with multiple links as well.
Is there like a signal or a signature for each person that you detect, or?
No, this is a collective behavior, and that's that we don't know anything, or we have no information about individual ones, just rather collective behavior in this area. Because if you want to do it individually, it becomes really hard. If you try to just like track individual people with Wi-Fi, with this setup, people have shown it up to 4 people. I mean, it's really difficult to go beyond to such high number. So what we spent, so these were our early results from a few years back, and more recently we've been looking at, can you do this through walls? And so we've extended our theoretical framework. It's a different methodology. It's actually more robust, also to a lot of noise, and also does not need much calibration. And so we've done a lot of tests with our behind wall counting over the campus. Here's a classroom. I have a transmitter here behind this wall and receiver here behind this wall. These are basically a Wi-Fi router and a wireless LAN receiver. And so there were 20 people here, and it counted it as 19. And in this particular case, we didn't need to actually, in this particular method we're using for behind walls, we don't really need to go to collect measurements in the same environment. Very small prior calibration phase that was done in a different environment in this case, which is promising. Because if you want to do behind walls, you may never know what is it. You may not be able to go there beforehand to collect prior measurements. And now, what if you add more links? That was a good question that was asked. So here, in this area, basically we're using these Sonos nodes, and now I have 2 links. And you can see that, and then we run several measurements here. Here I'm showing you the error plots. And basically, you can see that with one link, we had like 80-some% of the time error of 2 people or less. With 2 links, 100% of the time the error was 1% or less. So it was improved quite a bit. Now, if you throw in one more link here in this area, may not see much improvement at this point. But if you go over large spaces, then one thing we're looking at is how many links do I need? Because I want to do this with minimum number of links, as small as possible, while I still get the performance that I need. So those are some of the things we're looking at the moment.